Let's look at some examples of how we can find some possible inflection values. So we want to remember here that when we're looking for concavity and inflection values, we want to find any discontinuities first. Then we can look for those possible inflection values where f double prime, the second derivative, is 0, or when the second derivative does not exist. All right? So we're going to make a number line. We'll find the sign for f double prime, and we'll see when it's greater than 0, it's concave upward. When it's less than 0, it's concave down. So let's look for some derivatives here. So first, we got a sign problem here. So we take the first derivative, and that derivative sign is cosine of x. And then we're going to take the second derivative. Derivative cosine is negative sine x. So we want to find out when that equals 0. And we have a x is an element here of 0 to 2 pi. So that's its domain there. So when does sine equal 0? Well, equals 0 here at 0, pi, and back at 2 pi. All right, so x can be 0, pi, or 2 pi. And now we want to make a number line there. So 0, let's put 0 over here. 0, pi, 2 pi, all right? And let's see. When pick a number between 0 and pi over 2 would be a good one. So when we plug in pi over 2 here, into sign, we get positive 1, but then it becomes negative with that negative sign there. And something between pi and 2 pi, how about 3 pi over 2? And we plug in 3 pi over 2 here, we get negative 1, but this negative makes it positive. All right, so we're concave down when we're between 0 and pi, and we're concave up between pi and 2 pi. All right, and we have an inflection value at pi. All right, let's look at an expression here which has a product. Well, not really a product because we've got a 6 here. But we're going to find our derivative. Let's go ahead and find our derivative. F prime of x. Well, we're going to do a little chain rule here. So let's go ahead and take the derivative of the outside. Pull that negative 1 down. We get negative 6 times the inside. Subtract 1. We get negative 2. And derivative of the inside is 2x. Now I want to clean that up before we go any further. So let's multiply this negative 6 and 2x. And get negative 12x. X squared plus 3 to negative 2. I want to do that before you take the second derivative. So now we're ready to go ahead and take the second derivative with some product rule here. We could make this into a rational function and use a quotient rule. We could drop that down there. But kind of easiest to leave it up top, you'll see. So let's take the quotient rule, or the product rule, sorry. Let's use a product rule. Derivative of the first is negative 12 times the second. And plus the first, which is negative 12x, times the derivative of the second. I'm going to do the chain rule again. Drop that negative 2. X squared plus 3. Subtract 1. We get negative 3. Derivative of the inside gives us another 2x. Now we're going to have to solve this for 0. So we need to clean it up a little bit here. So let's combine some like terms that we can, or combine some of this over here on the second expression, second term there actually. Copy the first down for the moment. We're going to leave it as negative exponents for right now. And you'll see why. So let's combine that. Let's multiply that up. Negative 12 times negative 2, that would be 24 times 2. That would be positive 48. And x times x, x squared. Then we got the binomial x squared plus 3 to the negative third. Now, We could make this into a rational function by taking these negative exponents downstairs, but then we'd have to find a common denominator, and that gets a little trickier. An easier way to do this, and something that works better more often, is to factor. So we got two terms. So take a look at these two terms separated by a plus. Okay, and we want to ask ourselves, what do they have in common? Well, they both have a 12 or a negative 12. Let's pull out a negative 12. And then they both have an x squared plus 3. Now the question is, how many x squareds plus 3 should we pull out? Well, look at both terms. Now the key is, just like with always, we're going to pull out the smallest number. Okay, the smallest exponents. Now, which one is the smallest exponent? Watch out, they're negatives. It's this one over here. So we want to factor out x squared plus 3 to the negative third. All right, and let's see what's left over. So we're going to pull out the negative 12 from this term, and we're going to factor out x squared plus 3 minus to the negative third. Well, what do we do to those exponents? Because we're really dividing this from this. When we divide exponents, we subtract, or when we divide powers, we subtract exponents. So we got negative 2 minus negative 3. That's the same as adding 3. That's positive 1. Okay, now we're going to factor out negative 12 from this. That'll leave us with negative 4. And we're factoring out, we're going to leave the x squared, that is. So x squared will stay. And we factored out this whole expression here, x squared plus 3 to the negative third. So that whole thing got pulled out. So that's it for that second term. Now we're going to clean it up. So we want to solve this, is where we're headed. So now it's time to clean it up. And before we solve, we want to make it into a rational function. Okay, so now we're going to go ahead and drop this negative power down. And remember that negative 3 just deals with that binomial, just applies to the binomial there. And we're left with a negative 12 up top. And this whole thing cleans up. We don't need that first power, because first power doesn't change anything. X squared minus 4x squared. I believe that is negative 3x squared plus the 3. And there we have it. And, well, we could distribute that out, but that's going to be probably good enough there. All right, so we found our second derivative. So again, a couple little recommendations. One is, as we're working with this, leave it as negative exponents on those binomials. Probably best to avoid the rational function. You could do it. That's fine. If you feel like that works better, then make it a rational function and get common denominators. And then when we factor out the lowest exponent there. All right, now we did all of that, and we want to find out when this is 0. We want to set this equal to 0. All right, and so that happens when negative 3x squared plus 3 is 0. So when is the top 0? Well, really it's when this whole thing is 0. But, well, let's write it out. Negative 12, all right? And that negative 12, divide both sides by negative 12. We end up with negative 3x squared plus 3 equals 0. And if we subtract 3 and divide, we get x squared equals 1. And so x is square root plus or minus 1. Square root of 1 is 1. Don't forget your plus or minus when you square root both sides here. All right, so we're going to square root this side, square root this side. So we found 2 possible inflection values. We also need to look at the bottom. Will this bottom ever be 0? Can it be 0? Well, x squared here. Oh, sorry, one little thing too I caught here. Let's catch this. When we drop this expression down to the bottom, it becomes a positive exponent. Sorry about that. So that becomes a positive 3. Okay, it was negative up top, and now it's positive. All right, anyways, Will this ever become 0? No, it won't, because this can never be negative 3, because when you square a number, you only get a positive number. So that's it. So we found our possible inflection values. So let's make a number line. Let's plug -1 and +1. And let's test some values. Now it's easiest to test values into the factored version here. We need to plug it into f double prime. So I want to plug in this factored version. And you know what? I'm going to do one more thing just to make this easier. Let's factor out that -3. If we pull out a -3 from both of these, -3 times -12 gives us positive 36. We got 36 out here. X squared minus 1. All right. Now let's plug in a number to here, and you see it's a whole lot easier to figure out positive or negative. If you plug in positive 2 squared is 4, which makes the top positive. And the bottom, notice the bottom is always going to be positive, because when you square a number, it's positive, plus 3, it's positive, always positive. So it only matters what the top is. Plug in 2, it's positive, and again, the bottom is positive. Plug in 0. When we plug in 0, the top is negative. Plug in 0, the bottom's positive, so negative over positive is negative. Plug in -2. Plug in -2 over here. -2 squared is 4, minus 1 is 3, so that's positive. And again, the bottom is always positive. So positive over positive is positive. What that means is we have concave up, concave down, concave up. All right, so concave up is going to be from -infinity to -1. And from 1 to infinity, concave down is going to be from -1 to 1. And our inflection values happen at x equals plus and minus 1. All right. So a bit of work to get that second derivative, but that's the idea there.